Welcome to another video. In this video, we're going to be looking at a grade 9 paper written by a year 11 student. This was sent in by one of my lovely subscribers, so thank you very much for that. I love when I'm sent questions and exam papers and things like that, but I'm constantly surprised by the brilliance of the younger generations. I'm not that old myself, but those that are younger than me, I'm constantly surprised by their brilliance and their genius. I had a year 8 student the other day asking me about Euler and Euler's identity and talking about how they can cube any 2-digit numbers. I was floored. There's no way that I could do that stuff when I was that age, and I definitely couldn't have written this paper when I was 15 or 16, however old this student was. So as I said, this is a grade 9 paper, non-calculator. And when I first was sent this, I saw this down the bottom, John Lynch year 11, and I thought, okay, John Lynch, he must be some PhD mathematician. He's written this paper and he's put year 11 there to say that it applies to year 11 students. Then I later found out that actually this is a year 11 student who wrote this paper. So I was just absolutely floored and blown away. Because the questions in this paper are really, really good. There are a few minor criticisms I would have of some of the questions, but overall this is an excellent paper, and the fact that it's written by a year 11 student is absolutely amazing. But anyway, sorry for rambling on. I just wanted to share some of that excitement I had. But I won't be going through every question in this paper. I'll link the whole paper in the description if you want to look at it. I'll just be going through some of the questions that I find the most interesting, and also I'll link my worked solutions to every question. There's no messing around on this paper. Jump straight into the hard stuff, the good stuff. So question 1 says an office X is a small office. In the morning of day 1, the ratio of male to female workers in the office is 15:7. In the evening of day 1, the unsimplified fraction of male to female workers in the office is 35:25. 164 males entered the office at lunchtime and stayed for the remainder of the day. 184 females entered the office at lunchtime and stayed for the remainder of the day. Find the number of females that were in office X at the start of the day. Okay, so let's summarize some of this information first. So we've got the morning. The ratio of male to females is 15:7. Next, we've got the evening. The ratio then is it's 35:25. Let's go ahead and simplify that. If we divide it by 5, we would get 7:5. And then we've got this information here. We've got 164 men entered the office, 184 women entered the office at lunchtime. So what we're saying is that after we make those additions, we'll have this new ratio of 7:5. The next step for me, the most straightforward way of solving this would be to create an equation and then solve that equation to get to the answer. But there are other ways of solving this that are also fine as well. But one way of approaching this is to say that this ratio here, it doesn't represent the number of people in the office in the morning, but we could multiply each number by some factor, let's call that X, and then add them together, and that would give you the total number of people in the office in the morning. So we could also write that as a fraction 15x over 7x, right? So we have to multiply by some factor to get the actual number of people in the office. Then if we add on 164 males to the male part of that ratio and add on 184 females to the female part, this new fraction will be equal to the new ratio in the evening, which we could write as 7/5. Okay, so that's how we're creating an equation with one unknown that we can go ahead and solve for that unknown. So from here, you can cross multiply. So multiply this by 5 and this one by 7. So I'm going to do this in a couple steps because that's not so easy to do in your head. But let's write this as 5 times 15x plus 164. And then 7 times 7x plus 184. All right, 15 times 5, well, that's 75x. And then 5 times 164, that's going to be 500 plus 320. will be 820. 7 times 7 is 49x, and then 7 times 184, 700 plus. Okay, let's just go ahead and make sure we don't make any mistakes. Let's do a multiplication, a written multiplication here. 4 times 7 is 28, carry the 2. 8 times 7 is 56, plus 2, 58, carry the 5. 7 plus 5 is 12. Okay, so we get plus 1288. Okay, let's keep simplifying. We'll do 75 take 49. Difference of those is 26. X, and then 1288 take 820. Difference there is 468. 468. And then divide that by 26. That's kind of difficult. One way to do these types of divisions is to actually do it through trial and error. So think of what you might multiply 26 by to get 468. So usually I go up in tens. I'd do 10, 260. It's obviously not 10. Then I go to 20, 520. It's got to be less than 20. So then go down from 20, do like take 26, which is 194. Take another 26, 170, which would be 468. So then it's multiplied by 20, less 2, so it must be multiplied by 18. Sorry if I'm going into too much detail there, but it is a non-calculator paper, so I do think it's sometimes useful to talk about those non-calculator strategies. However, we get a value of x equal to 18. Remember what x is? It's what we multiplied this original ratio by. So we had 15x was the men in the morning, and 7x was the women in the morning. So go back to the question. It said find the number of females that were in the office at the start of the day. So then we need to do 7 times 18. 70 plus 56, 126 females. So question 1, and that was for 4 marks. All right, that was a good one. Next one, question 2. Question 2 says triangle ABC is shown in the diagram below. AC equals 3AB. Angle BAC equals 120 degrees, respectively. I'm not sure what that respectively means, but angle BCA equals theta. Show that angle BCA can be written in the form sine theta equals root A over B, where A and B are integers. All right, so let's write in a few things here. We've got the length AC is 3 lots of AB. Okay, so let's say those are in the ratio 3 to 1. BAC is 120, and then BCA is theta. Okay, and then we're looking for the sine of theta. Okay, so you'll notice we have 2 sides here and an angle between them. Well, we don't actually have the length of those sides, but we have as good as. So you could call this 3x and x, but it's essentially the same thing. And I'll point out why towards the end. But if we have 2 sides and an angle between them, usually that signifies you want to use the cosine rule. So we can use the cosine rule to find this side over here. Let's call that side A, and then we can go on from there. So let's firstly use the cosine rule to get A. So we can say A squared equals, let's actually just write out the cosine rule first. This is B squared plus C squared take 2BC cosine A. All right, then let's plug some things in. I'm not going to actually use this x. Again, I'll point out why towards the end, but we don't need it. So let's call this side B. So we'll have B squared is 9, C squared is 1, 2BC would be 6 times 1 will just be 6. And then the angle opposite A is angle A here, which is 120. So we'll have cosine 120. Let's go ahead and simplify. So this will be 10 take 6. Now here you need to know the absolute value of the cosine of 120. Now we can treat that as the reference angle. Now if you look at the angles on a straight line, for example, if we have 120 over here, we have 60 over here. Now I won't go into this in too much detail right now, but essentially when you're looking for the cosine of 120, it's the same as cosine 60, except we have a negative. So the cosine of 60 you need to know. You need to know absolute values of these angles, 30, 45, 60, and 90. I believe it's just those four. Cosine of 60 is a half. So then the cosine of 120 is the negative of that. So we'll have 6 times negative a half. So this becomes 10. Take 6 times negative half, well, this is like half of 6, which would be a negative 3. Subtract a negative 3 becomes a positive 3. So then we have a squared. Remember, this is a squared, so then a is going to be the square root of 13. All right, so we have a value for a. This is the square root of 13. Now we can go ahead and use the sine rule, or the law of sines. So this is called the law of cosines. We can go ahead and use the law of sines to help us find sine theta. So we can say that sine of 120 over root 13 equals sine of theta over 1. That's the law of sines. Now we also need to know the absolute value of sine 120. Again, it's the same as sine 60. So sine 60 is root 3 on 2. Now when you're talking about sine of 60 and 120, they're both positives. So it's not like cosine of 120 and 60 where one is negative, one's positive. These are both positives. So now we need to plug in this root 3 on 2 into here. So we'll have root 3 on 2, and this is multiplied by 1 on root 13, and this is equal to sine theta on 1, which is the same as saying sine theta. Then we'll have sine theta equals root 3 on 2 root 13. Now we need it in this form where we have root a over b, so we need to rationalize the denominator, multiplied by root 13 over root 13. Then we get 3 times 13 on the top line would be the square root of 39. On the bottom line, we'd get square root 13 times square root 13, that's just 13, times 2 would be 26. So I believe that should be the final answer, 39 being a product of two prime numbers, 3 and 13. We can't factorize that into any square numbers, and so we can't simplify any further. So sine theta equals root 39 on 26 there. And that was a question for 7 marks. No messing around on this paper, straight into the hard stuff. Okay, this is the next question I wanted to go through, question 5. It says the measures of the interior angles of a convex hexagon form an increasing arithmetic sequence. How many such sequences are possible if the hexagon is not equiangular and all the angle degree measures are positive integers less than 150 degrees? So when it says convex hexagon, that means that all the angles are less than 180. So we can't have, angles like this, for example. So we could draw a 6-angle shape somehow. So that's 1, 2, 3, 4. Is that 6? 1, 2, 3, 4, 5, 6. So that would be a hexagon technically, but that would not be a convex hexagon. All right. So we've got a convex hexagon with the angles in an increasing arithmetic sequence. So firstly, I want to draw what this might look like. So it doesn't say regular hexagon. So it wouldn't look, it might not look anything like this. In fact, it probably wouldn't look anything like this, but this is just to represent kind of what's going on. So we'd have our first angle. This could be anything. Let's call that X. Then to get the next angle, we would add on some integer, because it says, where is it? The angle measures are positive integers, so we must be adding on an integer. So we'd have x plus n. Then this next one, well, in arithmetic sequence, we always add the same thing. So this third angle would be x plus 2n. The fourth angle, maybe you can see what we're going to do here. We'll do x plus 3n, x plus 4n, and the final angle would be x plus 5n. So that's essentially what's going on. The angles are slowly getting bigger and they're in an arithmetic sequence. Now, we want to find how many such sequences are possible. All right, firstly, what I want to do is to find the sum of angles in a hexagon. So we can do that using the sum of angles formula for a polygon, which is n take 2 times 180. This would be 6 take 2, this n being the number of sides. So 4 times 180 is 720 degrees. And then let's find the sum of all these things. So if we add these up, well, we'd have x plus x plus x plus x plus x would have 6x. And then we'd have n plus 2n plus 3n plus 4n plus 5n. Add all of those up, you get 15n. And this needs to equal 720 because they must add up to the interior angles of a hexagon. All right. So this is, if you like, my first equation that I've created. Next, let's go back to the question again. And it says, all the angle measures are less than 150 degrees. So let's take this biggest one here. That's all we really need to worry about. And we can say that, which is x plus 5n, that needs to be less than 150. All right, that's like my second sort of equation. Well, it's an inequality, really, but it's going to help us to prove how many sequences are possible here. Firstly, what I'm going to do is to find some limitations for x. So, and we can do that by rearranging these two formulas. So let's look at number 1, equation 1. If we divide through by 3, we would get 2x plus 5n equals 720 divided by 3. That's 240 because 72 divided by 3 is 24. And then we could say, actually, let me just move this down a little bit. Then we could say that 5n equals 240 take 2x. Okay, next, let's rearrange this one slightly. We can say that 5n is less than 150 take x. And then let's combine these two ideas and say that, therefore, 240 take 2x is less than 150 take x. And then rearrange to solve for x. So if we added x to the right hand side, we'd get added negative 2x, and then take 150 from the left hand side, we get 90. So we know that x must be greater than 90. And that's just one way of showing that, but it's a helpful start. So the start of this sequence of 6 numbers has to be greater than 90. Next, I want to go back to this equation. This 5n equals 240 take 2x, and I might move all this stuff down again. So move this down. Then we can say that n equals 240 divided by 5. That's going to be 48 take 2 on 5x. All right, now this is the interesting part here. This 2 on 5x is the interesting part of this equation. Why is that so interesting? Well, remember the conditions of n and x, they had to be integers. So all of the angles, they have to be positive integers. Therefore, x must start as an integer and we must be adding on integers. If we're adding on a fraction here, the second angle would be some fraction, would be some rational number. So therefore, it wouldn't fulfill these conditions. So n must be an integer, x must be an integer. Therefore, in order for n to be an integer, x here in this equation, it must be a multiple of 5, right? If we divide by 5, we need to get a whole number. So this is telling us, this piece of information here is telling us that x must be a multiple of 5 because it needs to divide by 5 evenly. All right, so we can combine that information to say, Well, it needs to be greater than 90. It needs to be a multiple of 5. And this is not greater than or equal to. Keep that in mind. This is greater than. So we need to start at a multiple of 5 greater than 90. So the first thing we can start with is 95. So these are possible values for x. Next multiple of 5, 100. Next multiple of 5, 105, 110, 115. Now I'm going to stop at 120. Why do you think I stop at 120? It's because 120 is the angle in a regular hexagon. All right, so once we get to 120, we're looking at a regular hexagon. If I go above this, there's no possible way I could have the angles in that hexagon adding up to 720. That'd be more than that. So I'm going to stop at 120. All right, now we can also, if we've got the first value of x, we can also find n, right, using this equation. So sub in x to this equation here. 95 divided by 5, that's going to be, well, 1 less than 20, 19 times 2, 38. 48 take 38 is 10. That means n is 10. Remember what n was? That was what we're adding to each angle. So this sequence, we're adding on 10 each time. So we get 105, and then 115, and then 125, 135, and 145. So now, because we've obeyed all of these rules, we figured out this sequence should add up to 720. And it should be a possible sequence for this hexagon. So if we add these up, this would be 200, 315, 440, 575, 675, plus 45, that is 720. Okay, so this is a possible sequence. And then we just need to apply these rules to each one of these numbers. 120 is not going to be one. I just wrote that down as an endpoint. But each of these should be a possible sequence. So if we do 100, 100 divided by 5 is 20, times 2 is 40, 48 take 40 is 8. So we'd have n being 8. So we get 108, 116, 124, 132, and 140. Add those up, we would get 720. And I am just so confident in this maths that I'm not going to even check the rest. I'm just going to say there's 1, 2, 3, 4, 5 possible sequences, 120 being where we'd have a regular hexagon. So my answer there to how many such sequences are possible would be 5 sequences. Okay, so that's one way you could go about proving this. I think there are probably plenty of other methods of doing that question. That's what I kind of love about this paper and these questions. Good questions always have multiple solutions. I mean, again, excellent work from a year 11 student. Okay, this is the next question I want to go through, question 7, and probably my favorite question from this paper. It says, a triangle in the coordinate plane has vertices at -4, 0, 9, 0, and 0, 7. The line y equals 7 on 4 x plus c, where c is a positive integer, divides the triangle into a trapezium and a smaller triangle whose areas, respectively, are in the ratio 7 to 9. What is the value of c? Express your answer as an improper fraction in the form a over b. Now, if you haven't had a go at this paper, I strongly advise you to have a go at this question. So please, if you haven't attempted it yet, pause the video now before I go through my explanation and have a go. All right, so let's firstly draw a diagram. So let's draw up the coordinate plane, and we don't need really anything in the negative y direction. So let's just stop there, and we'll have -4, 0, 9, 0, be up here somewhere, and then 0, 7. Sorry, that'd be 0, 7. This would be 9, 0 over here. Okay, so we've got a triangle like this. And then we have some line, y equals 7 on 4 x plus c, where c is a positive number. Now remember what c is in this equation. C is the y-intercept. Okay, so this would be where the line cuts the y-axis. So if that's positive, then it's going to be cutting the y-axis above the x-axis. And it divides this larger triangle into a trapezium and a smaller triangle. Okay, so now we need to look at this slope, 7 on 4. That's a positive slope, so the line's going in this direction like this. It has, as we've said, a positive y-intercept. So to split this into a trapezium and a smaller triangle, it would have to look something like this. Okay, something like that. This would be the smaller triangle. This is the trapezium here. And the area of these two shapes is 7 to 9. Okay, and we're looking for C. Again, that would be the y-intercept, this point here. All right. Again, plenty of ways to answer this question, but I think most of them need to start with this ratio here. So if this trapezium to this triangle is 7 to 9, that means the larger triangle to the smaller triangle, that ratio would be 16 to 9. So let's start off with that. Let's say, actually, let's label these points A, B, C, D, and E. So let's say the area, let's start down here actually, area of triangle ABC to the area of triangle DEC. This is going to be 16 to 9. I think that's an important place to start. Then you need to think about the properties of a trapezium. So one property of a trapezium is that the top and the bottom are parallel. Okay, so these two lines here, they must be parallel. Okay, AB and DE. Also, because these two lines, the x-axis and this line BC, they can't possibly be parallel, right? So it must be AB and DE. So that's the next thing we can note. So as ABD is a trapezium, AB and DE must be parallel. What that tells us is that these two triangles, this larger triangle ABC and DEC, they must be similar. And you could use, for example, the idea that all the angles are the same. So these angles must be the same due to the parallel lines. They would be corresponding angles. These angles must be the same, again, corresponding, and this one is the same because it belongs to both triangles. So we can say, therefore, triangle ABC and triangle DEC are similar, angle, angle, angle. And then you need to know about some properties of similar shapes, particularly the ratio of the sides and the ratio of the areas. So for example, if we're talking about the base of these triangles, so base 1 being the base of the smaller triangle, this is equal to the square root of the area of the first shape divided by the area of the second shape. That's if they're similar shapes. Okay, so now we have the ratio of the areas, 16 to 9, or 9 to 16 if you wrote it around the other way. Therefore, we can say the ratio of these lengths would be the square root of 9 over the square root of 16. Square root of 9 is 3, square root of 16 is 4. So now we have the ratio of the lengths. And we also know the length of the base of the larger triangle because we have these points. A was at -4, 0. C was at 9, 0. So that length is going to be 9 plus 4 essentially, that length there. 9 plus 4 is 13. So then we can say that therefore the base of the smaller triangle divided by 13 would equal 3 over 4. And then the base of the smaller triangle would be 13 times 3/4, or 3/4 times 13. 3 times 13 is 39 on 4, which you could also write as, well, 36 divided by 4 is 9, with 3 left over, so you could write that as 9 3/4. Okay, so that's the length of the base of the smaller triangle. So let's actually just indicate where that is in red. So that would be this length here. So we've worked that out to be 9 3/4. What does that mean? Well, this coordinate here, this x coordinate is 9, So that's the distance from O, the origin. That means this little distance here, this little distance from O to this point, where that line cuts the x-axis, that must be 3/4. So the x coordinate of where that line cuts the x-axis is 3/4. Okay, so now we have a point on that line and we can go ahead and solve for c, and we can do that in a number of ways. All right, so once you get to that point there, working out the fact that you need to use that ratio of the areas to work out the ratio of the side lengths, I think that's the main difficult part of this question. But let's keep going. So we know that point D, so therefore D must be 3 on 4, 0. So then we can say using this point, the equation of the line, which is y equals 7 on 4x plus c, you can insert those numbers into this equation. So y is 0, right? These are the x and y coordinates. They fit into this equation where the y and the x are in this equation. Y is 0, we'd have 0 equal to 7 on 4 times 3 on 4, which is the x coordinate, plus c. Sorry, that's a negative 3/4, my apologies there. So this is negative 3/4. And then we would get 21 on 16, negative 21 on 16, add that to the other side, c equals 21 on 16 for a final answer. And there are a couple ways to finish that off once you get this idea that the base is 9 3/4. Another really nice way is to look at these two triangles. So these two right angle triangles here, and notice that they are similar. Now remember, point B was 0, 7. So using the idea that they are similar, you can say that the ratio of those two lengths, so 7 on 4, the height over the base, 7 on 4 equals the ratio of this little triangle here. And the height would be the y coordinate there. So this would be c, actually, divided by 3/4. And therefore, c would equal, multiply 3/4 on the other side, we'd get 7 on 4 times 3 on 4, and we'd get 21 on 16. So that's another really nice way of finishing that problem off that I thought I'd point out. But there you go. Probably my favorite question from this paper. Really an excellent question. This could easily come from a GCSE higher exam, but the fact that this was written by a year 11 student just makes it that much more incredible. So really an excellent question. Okay, question 9. I'm not going to go through question 9, but I just want to point out that it should say, I mean, there are actually two answers to this. So when it says what is the value of y to the negative x, it should say what is one value or what is the rational value or something. So slight criticism there for question 9. Okay, question 10 says a bag contains 52 marbles. A quarter of these marbles are blue, 3/26 of these marbles are red. The remainder of the marbles in the bag are white. How many white marbles must you add in the bag so that 39 out of 42 of the marbles in the bag are white? Okay, so firstly, let's work out how many are blue. So we'd have a quarter of 52, that's 13. Then we have 3 out of 26 are red. Well, 26 is half of 52, so we'd do 56 divided by 26 is 2 times 3 would be 6. And then the remainder are white. So this adds up to 19. 52 take 19. Well, let's just write down what we're working out. Then we'd get 33. Okay, so the next step is similar to the first question actually. So I think the most straightforward way of solving this is to create an equation, but you have to be careful because we need to add white marbles so that it equals 39 over 42. So that's what we need to finish with. We currently have 33 white marbles. So we could do 33 plus some number x divided by 52 equals this. and then solve for x and we'd get the number, right? Not quite. Don't miss that if we add white marbles to the number of white marbles, we also need to add the same amount to the total marbles, right? Because however many we add, we're adding to the total. So if we added 5 white marbles, we'd have 38 white marbles. We'd also have 5 extra marbles in total. So that's the little trick to this question that I think is difficult to maybe get or difficult to figure out, is that you need to add the same amount to the number of white marbles and the total. Once you've got this, you've got an equation you can solve for x and eventually get to the answer. So let's go ahead and try to solve this now. So the first thing you could do is to cross multiply. So what you're going to have here is 42 times 33 plus x. So I'm going to do some operations over here. 42 times 33, 2 times 3 is 6, 4 times 3 is 12, do the tens. This would be 1260, add those together and we get 1386. So if we multiplied 42 by this, we get 1386 plus 42x. Then on the right hand side, we will have 52 times 39. Again, another multiplication over here. 2 times 9 is 18. 5 times 9 is 45 plus 1, 46. Then 2 times 3 is 6. 5 times 3 is 15. Add these together, we get 2028. Okay, so on the right hand side, we'll have 2028 plus 39x. Keep simplifying, so take 39x from the left hand side, we'd be left with 3x. Then on the right hand side, we'd get 2028 take 1386. Well, because I don't want to make any mistakes, I'm going to write that down as well. So 8 take 6 is 2, borrow 1, 12 take 8 is 4, 19 take 13 is 6. So this is going to be 642. And then x is going to be 642 divided by 3. That's going to be 214. Okay, so remember x was the number of white marbles we wanted to add, so that's our final answer there, 214 white marbles. Okay, question 15 is the last question I want to go through. Again, apologize if you wanted me to go through every single question. I just wanted to go through the ones I thought were the best or the most interesting, and also the worked solutions to all the questions are in the description if you want to see those. So final question here, question 15 says, find all positive integers of n for which n squared plus 60 is a perfect square where n is not equal to 0. Use these integers to obtain the value of x cubed, where x is the product of all the possible values of n. So part of the difficulty of this question is actually trying to interpret what the question is asking, but it's saying that we want n squared plus 60 to equal a square number. So what's one way of writing a square number? It's some other number squared, right? So square numbers, what am I talking about? Well, 1, 4, 9, 16, 25, 36. They're the square numbers or perfect squares. And then another way of writing those is 1 squared, 2 squared, 3 squared, 4 squared, etc. Okay, so here to represent that it's equaling a perfect square would be to write a squared. In order to help us solve this, we can rearrange this slightly. So I'm going to subtract the n squared from the right hand side and rewrite this as a squared take n squared equals 60. Now again, you might be thinking, this isn't very helpful. How am I going to figure these things out from this equation? Well, again, there's a slightly different way of writing this. This is known as the difference of two squares, and you can actually factorize this expression, and you can write it as a plus n multiplied by a take n equals 60. So if you expand this out, you'll get a squared take n squared. Now this is useful because it tells us that these two things need to be factors of 60 in order for this to work. Now remember also that they all need to be integers. So n is a positive integer, they've told us that. To get a perfect square, a needs to be an integer. So we're only working with whole numbers here. So these two things, these two numbers need to be factors of 60 and they need to be integers. So one way to figure this out is to write down the factors of 60. So 60 equals, well, 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and 6 times 10. 7 doesn't go, 8 doesn't go, 9 doesn't go, and 10 we get back to the start. Okay, so these are all the factors of 60, and these are essentially all of the things we need to worry about to solve this equation. So now we want numbers that add together to make one factor, and their difference needs to be the other factor. And there are some shortcuts you can take here. So what we're actually working out here is, well, we'd have a plus n equals one of the factors, and then a take n equals the other factor. So let's just put in an example. Let's say we had 60 and 1. So are there two numbers that make this? Well, this is like a set of simultaneous equations, right? And one way to solve this would be to add these equations together. A plus a is 2a. N plus negative n, they cancel out, that's the whole point. And then 60 plus 1 is 61. Then we get 2a equal to 61. Because 61 is not an even number, it won't divide by 2 evenly, therefore a would not be an integer, therefore this is not a possible solution. So we don't have two integers that would work for this equation here. And now we have a little shortcut. We can say that 2a would equal these two things added together. So 2a, for this case, we'd have 2a equal to 32. Therefore, a would equal 16. And now let's see if this one works. So plug a into either of these equations. So now we're working with 2 and 30. So 30 and 2. A 16 plus something needs to equal 30. Well, that would be 14. And 16 take 14 would be 2. So these factors here, they actually work for our equation over here. So one possible solution of this is, well, looking back here, we would say that a equals 16 and n equals 14. So I just want to go back to the question. It says find the integers of n. So the solution we're actually looking for here is n. We don't really care about a, that's kind of to the side. It's kind of unconsequential, if you like. Okay, but let's keep going with this. If we look at the factors 3 and 20, we would have 2a equal to 23. Again, we don't get an integer value of a, so that's not going to work, just like this one up here. So this is no good. Next one, once you see kind of, or get the understanding of what's going on, you can kind of do it in your head. So 4 plus 15 is 19. Divide by 2 won't be an integer, so that's not going to work. Again, 5 plus 12 is not going to work because we get an odd number. And then 6 and 10. Let's try 6 and 10. We'll add those together. Would be 16. Then a equals 8. Let's plug this into our little algorithm down here. We would have, well, they would add together to make 10 and subtract to make 6. If a equaled 8, n would be 2. Then we get 8 take 2 equals 6. So this then would work if a equals 8 and n equals 2. So we have another solution. We have a equal to 8 and n equal to 2. And We've gone through all the factors of 60 now, so therefore these must be the only two solutions. They're the only things that satisfy this equation up here. So therefore, all the positive values of n, which would make a perfect square, are 2 and 14. Then we need to find x, where x is a product of all the possible values of n. So x is going to be 28. And then we need to find x cubed. All right, so I guess we just need to do 28 times 28. Okay, so this is something that I probably wouldn't include in a non-calculator paper. But then again, I'm not completely masochistic. So if you are, maybe you prefer these types of problems where you just are mindlessly kind of multiplying things together. But let's keep going now. 784 times 28 again. Okay, so then I end up with 21,952. So x cubed, 21,952. All right. Now there might be a shortcut to cubing numbers actually. I think there is. If you know one, let me know in the comments. But again, yeah, that was the final question that I'm going through on this paper. I hope you found that useful. I certainly found that enjoyable to see such a paper written by a year 11 student. Let me know what you think in the comments. If you appreciated this video, please leave a like. It means a lot to me if you leave a like on the video. Subscribe if you want to see more content, and I will see you in the next one. Bye for now.